and angle bisectors. So you're going to learn a couple theorems and then the converses of those theorems as well. But I feel like this lesson is one of those, like, when in doubt, set them equal to each other. So keep that in mind as you go. Let's say we have this situation. We have a segment, and we have the perpendicular bisector, so perpendicular and bisector of that segment. We'll call this segment AB, and we'll call this D for now. If I were to put a point C up here and turn it into two triangles, what do you know about those two triangles right now? They're congruent. By what? By SAS, right? This is reflexive. This would be the same. So you have side angle side and side angle side, right? So if I have a perpendicular bisector and I pick a point on that perpendicular bisector, I get two congruent triangles, which means if my triangles are congruent, everything about them is congruent by what? CP-CTC, right? Back to chapter 4. So that means that AC would be congruent to CB, okay? And that is our first theorem for today, is that it's called the perpendicular bisector theorem. The perpendicular bisector theorem. And it says this: if a point is on the perpendicular bisector, the point is on the perpendicular bisector of a segment, then it's equidistant. Equidistant. Do you know what that means? Equal distance. Okay, so it's the same distance away. It's equidistant from the endpoints of the segment. Okay, so essentially what it's saying is that picture up above. If a point, so point C, for instance, is on the perpendicular bisector, which point C is, then the distance to the endpoints, to A and to B, has to be the same. Okay, so I could pick a different point. I could pick a point E down here, and I would know that the distance to A is the same as the distance to B. Okay, so any point on the perpendicular bisector will be the same distance away. That's the perpendicular bisector theorem. There's also the converse to it, and the converse is just switch your if and your then portions, right? So if a point is equidistant from the endpoints of a segment, then it's on the perpendicular bisector of the segment. I'm not going to write that one out. Just note maybe that there is a converse to this as well. You guys know what a converse is by now. You just flip-flop it. That's the converse, okay? So there is a converse. We're not going to write it. You're welcome to if you want. I'm not going to write it, okay? Any questions on that? Okay, so if that's our theorem, then here's a problem to illustrate it. Let's say we have triangle MNP, and this is point O, and it's marked perpendicular and those parts congruent. Okay, and they're going to ask, what is the length of MN? And they give us this. This side is 6x minus 1. This side is 3x plus 8. So that's all our information. What you need to take note of is that we have a perpendicular bisector, right? This is perpendicular, and this bottom side, NP, has been bisected. So if we have a perpendicular bisector, then this, any point on that perpendicular bisector, what's our point that's on the perpendicular bisector? There's two, actually. M and O are both on the perpendicular bisector, okay? So that would mean that point M has to be equidistant to N and to P. So in other words, this distance has to be the same as that distance, okay? Yes?
Because both of the MN and NP are congruent, does that mean we're going to use a bunch of isosceles triangles later too?
You could use all of the rules of the isosceles triangles with that. We don't do a ton with it, just because we already did that stuff, but you definitely could. Yeah, it's going to be isosceles. Okay, so in this setup, if we want to know the length of MN, we're just setting 6x minus 1 equal to 3x plus 8. And like I said, when in doubt, you set them equal in this lesson. It's a lot of congruent parts, okay? So we're going to solve this, take away the 3x, add the 1, and you get 3x equals 9. Divide by 3, you get x equals 3. But they didn't ask for x, they asked for mn. What is mn?
Oh.
17, right? So you would take 6 times your x value minus 1, or 17 for the length of mn. Okay, set them equal to each other. All right, so a little more real world with this. You're at, what's your favorite theme park? Disneyland, okay? What's your favorite attraction at Disneyland? Cotton candy? Okay, so here's a cotton candy machine. And what's the other one? Someone else said something. What? Say it. Magic Mountain. Oh, your favorite theme park is Magic Mountain. Okay, something else at Disneyland. Or is there a Magic Mountain at Disneyland? There is?
Oh, that.
Which one?
Matterhorn.
The Matterhorn? Okay, the Matterhorn. All right, so let's say there's a guy selling those little, like, you push a button and it lights up and spins. That's what my kids got from Disneyland the last time we were there. They were a hit. So he sells that, but he wants to be placed perfectly between the cotton candy and the Matterhorn. He wants to be equidistant from both of those. Where could he put his booth?
In the middle.
Directly in the middle. So he could put one here, let's say, right? If we were to make this a segment. Oh, that's bad.
You can put it anywhere along the perpendicular bisector.
There you go. That's what we're looking
So
for.
we could put it 1,500 miles away.
Yep, and he would be
Disneyland.
equidistant. All right, so he could go right in the middle of this, right? He could put it right there, and he would be equidistant from the two. But, like Daniel said, he could put it anywhere on the perpendicular bisector. So that means anywhere on this green line here. I'll try and make this look. He could. That would be ridiculous, but he could. So anywhere on that green line would be the same distance to the cotton candy as it is to the Matterhorn, right? So a point here, a point here, a point here. Any of those would be the same distance away. This would be the same, or this would be the same, right? So anywhere on that perpendicular bisector is a good place if he wants to be equidistant. Questions on that? Okay, for the next thing we're going to talk about, and you'll do this at times throughout the lesson as well, but they're going to at times talk about the distance from a point to a line. Sorry, my ruler's in the way here. Let's move this. Okay, when they talk about the distance from a point to a line, let's lay this out like this. You have a point, and you have a line. Okay, if I said the distance from that point to that line is fill in the blank, you could all give me a different answer if we didn't have a way of defining that distance, right? Because you could say, oh, I think the distance is from here to this point over here, or I think the distance is from here to this point over here, or I think it's from here to here, okay? So you could all give me a different length. Therefore, so that we avoid that confusion, the distance from a point to a line is always going to be perpendicular. Okay, so whenever they talk about the distance from a point to a line, you want to make sure you're going perpendicular from the point to the line. Okay, so in other words, the distance from this point to this line would have to be this right here. Okay. Whatever that length is when it's perpendicular would be that distance away. So just make sure when they're talking distance from a point to a line, you're thinking perpendicular, and you'll be great. That means if I had a point over here, the distance from that point to the line would have to be this, right? We'll call that y for now. Okay? So using that idea, I have another theorem for you, another bisector theorem. This one, instead of a perpendicular bisector, we're going to talk about an angle bisector. So let's lay that one out. This is called the angle bisector theorem. And it really is saying a very similar thing to the perpendicular bisector theorem, but with angle bisectors instead. Here's what it says. If a point is on the bisector of an angle, if a point is on the bisector of an angle, then the point is equidistant, which means what again? Equal distance, right? The same distance away. Then the point is equidistant from the sides of the angle. And again, this one has a converse. I'm not going to write the converse out. You just flip it around, right? Both will be true. But here's what that's saying. If I have an angle, we're going to make them nicer. Hold on. All right, so I have this angle, and I have an angle bisector. This ruler doesn't want to do an angle bisector for me. Okay, well, you know what? No, we're just going to freehand it because it doesn't want to. All right, so you have an angle bisector. What it's saying is any point, because it's on the angle bisector, any point on that bisector, so like this point here, should be the same distance away from one ray as it is from the other. How do we calculate distance?
Perpendicular.
Perpendicular. So I would have to go perpendicular here and perpendicular here. So basically what it's saying is this length is the same as that length. Okay? Or I could pick another point. I could pick this point here. And as long as I go perpendicular and perpendicular, then this length is the same as that length. Okay, so as long as it's on the angle bisector and you go perpendicular to the angle, the distances should be the same. Okay, here's what you're gonna do with that one. Okay, if you look at this picture, before I give you any measurements or anything, can you tell me what we know to be true because of the angle bisector theorem?
BF is congruent to FE.
Right, the distance from the point on the angle bisector, so from point F, the distance to our two rays should be the same. So in this problem, they're giving you that this is 5x and that this is 2x plus 24. Okay, you just have to identify that, oh, those are going to be congruent, so what do you do with them?
You solve
How?
by
By setting them equal, okay? When in doubt, set them equal. So we're gonna say 5x equals 2x plus 24. So take away your 2x, you get 3x equals 24, divide by 3, and you get x equals 8. Okay, now you can always go back and check it if you plugged it in. 5 times 8 is 40, so the length of this segment is 40. 2 times 8 is 16, plus 24 is 40, so it checks out, so you know they're the same, which means you know it's correct. Okay? Were you going to tell me something else?
Well, yeah, could you also just say that they're congruent by HL and then, oh wait, no, never mind, you can't do that.
It would actually be angle, side, but you would have to first say that the two right angles are congruent angles, and then, but yes, then CP/CTC would make them congruent, which is how they come up with these theorems in the first place. So it's pretty much just a shortcut to not having to do a proof like that every time.
Okay.
But yes. Questions on that?
Nope.
Okay, just pay attention to if they're asking you for the variable or they're asking you for a length. Don't stop at the variable. If they want to know, like, what is the length of BF, make sure you plug it in and go the rest of the way with that. All right, that's it.